Welcome back, students, to the chapter Some Basic Concepts of Chemistry. Today we will see the part 5 of its theory. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. Our objective for today's class would be learning how to calculate the mass percent of a component element which is constituting a compound. Then we will try to learn about empirical formula and molecular formula with the help of experimental data. Lastly, we will see how to perform stoichiometric calculations. So first point that we would cover is percentage composition. Then empirical formula for molecular formula, in-text questions, stoichiometry and stoichiometric calculation, limiting reagent, reaction in solutions, mass percent, mole fraction, molarity, and molality. So these are all the topics that we will cover under our objective. The first thing that we will learn is percentage composition. For example, if we take water, we know that it contains hydrogen and oxygen. Now, the percentage composition for both of this can be calculated as mass percent of an element is equals to the mass of that element in the compound by molar mass of the compound into 100. So we know that the molar mass of water is 18.02 gram. Therefore, mass percentage of hydrogen can be calculated as, so in 1 mole of that element, 1 mole of that compound, we will have 2 gram of hydrogen. So this mass which we are talking about in the numerator is the mass which is present in 1 mole of the compound, because we are taking the molar mass. We are taking 1 mole of the water molecule, and 1 mole of water molecule will contain 2 moles of hydrogen whose mass is 2 gram. Okay, multiplied by 1.008. So this whole thing, which is 2 into 1.008, is the mass of hydrogen. Now we have taken a very accurate value for the atomic mass of hydrogen. Multiply this thing by 100, you will get 11.18%. The same calculation can be done for oxygen. So oxygen has 1 atom in the water molecule. So in 1 mole, it will have 16 gram. The total mass is again 18.02. Therefore, multiplying it by 100 gives us the mass percentage of oxygen is 88.79%. So it's very easy to calculate. You can just use our formula. So it is the given by mass of the compound, molar mass of the compound in the denominator, and mass of that element in the 1 mole of the compound multiplied by 100. Next, we can do the same calculation for ethanol. How we'll do it? The molecular formula of ethanol is C2H5OH. Ethanol, it has 2 carbons and 1 alcoholic group. What will be the molar mass of ethanol? 2 carbons will contribute 2 into 12.01. 5 hydrogens will contribute 5 into 1.008. There is one more hydrogen here, so it will be 6 into 1.008. Lastly, oxygen is 16. Okay, this will give you the molar mass equals to 46.068 gram. Now we will calculate the mass percent of each of the element one by one. So the contribution from carbon was 2 into 12.01, which is 24.02 divided by the total mass. So it is just a simple calculation of percentage like you do in your exams for your marks. Here we are doing it for the mass percent of carbon. This thing multiplied by 100 gives us 52.14 percentage of carbon. Moving on to hydrogen. So hydrogen contribution can be calculated by multiplying 6 with 1.008, which will give you 6.048, divided by again the molar mass or the total mass in 1 mole of ethanol, which is 46.068, and this whole thing is multiplied by 100 to convert it into percentage. It will give you 13.13%. Our last element is oxygen. So oxygen has a mass of 16 gram in this 1 mole of ethanol, and 1 mole of ethanol has a mass of 46.068 multiplied by 100 gives us 34.73%. Now, if you are asked to rearrange the percentage composition of these three elements, how you will do? It's very easy. We have calculated the percentage. Just keep hydrogen with the least percentage contribution and carbon with the most percentage contribution, whereas oxygen will be the mediate one. So these are the two examples. If you are able to understand, then you are good to go with this percentage composition thing. Now, why we have learnt about this percentage composition? Because it will help you to calculate or to find out the empirical formula for different molecular formula. If I define empirical formula, then it represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula tells us about the exact number of different type of atoms. So empirical formula is the ratio and molecular formula is the exact number present in a molecule. Now, if you have the mass percent of various element, then you will be able to calculate empirical formula very easily. So the percentage composition that we have calculated for each element, if we know that, then we can know the empirical formula, but not the molecular formula. But again, if you have the molar mass also, then you can get this molecular formula with the help of the molar mass. Clear? Now, let us try to understand this whole thing and the whole funda of empirical and molecular formula and its calculation with the help of a question. So, I will give you the solution step by step and I will try to explain each of the step minutely. First, we have hydrogen percentage, carbon percentage and chlorine percentage given already. So, I have already told you that if you have the percentage composition of every element present in a compound, then you can have the empirical formula. So, the first goal is to calculate that thing only. Second thing I have told you that if you have this data plus the molar mass thing, then you can get the molecular formulas as well. Now, what is the method for that? We will see it. The first thing that we will do is the conversion of mass percentage to gram. What do you mean by percentage if I ask you? So, by percentage, we mean that if we are taking 100 gram of the compound, then according to this percentage composition, we will have 4.07 gram hydrogen, okay, 24.27 gram carbon, and 71.65 gram chlorine. So that is the very basic meaning of percentage. So basically you take 100 part of it, okay. So here we are taking 100 gram of the compound, and with the help of this gram, we know that our contribution from every element is their percentage. Okay. So now we have the amount of hydrogen, carbon and chlorine present in 100 gram of the compound. Our next goal would be to convert this mass into moles. To do that, we will simply use our formula, which is given mass by molar mass. If you do that for hydrogen, the given mass is 4.07 gram and the molar mass is 1.008 gram for hydrogen. After calculation, you will get the number of moles as 4.04. Next, we will do it for carbon. So carbon has a molar mass of 12.01 and the given mass is 24.27. Again, putting the values, we will get 2.021 as the number of moles of carbon in 100 gram of the compound. Remember, we have the mass in 100 gram, so we are getting the moles in that same 100 gram. Now for chlorine, 71.65 by 35.453, which is 2.021. So we have the number of moles for each of this. Now, can we get the empirical formula from here? Let's see. To do that, what we will do? We will divide each of the mole that we have obtained with a smallest number amongst them. Obviously, the smallest number amongst them is 2.021. If we do so, then we will get 2 for hydrogen, 1 for carbon and 1 for chlorine. Okay, so we have taken the number of mole and we have divided it by the smallest number among these 3 moles only. So among these 3 moles, 2.021 was the smallest. If you divide it, you will get approximately 2 for the hydrogen, 1 for the carbon and 1 for the chlorine. Now we can write the empirical formula. If suppose after dividing you are not getting a whole number, so here we are getting a whole number 211, but if you are not getting the whole number, then you have to multiply this ratio by a suitable coefficient. Suppose you are getting 1 by 2, 1 by 2 and 1 by 2 instead of this 211. Then you will multiply the whole ratio with 2. Then you will get the same ratio as 1:1:1. So this is the idea behind multiplying. Now why are we multiplying it? Because you will never get a fraction in this empirical formula. You will always get a whole number. Now we have correspondingly 2 hydrogens, 1 carbon and 1 chlorine. Therefore, CH2Cl is the empirical formula. Now this is the simplest ratio for the stoichiometric thing. Okay. But this is not the actual molecular formula, because in molecular formula, we find the actual number of atoms present in one molecule of that compound. But here we are taking a ratio of that count. So how we'll do it? We have the molar mass thing still left in our pocket. So first of all, to write the molecular formula, we have already determined the empirical formula. Now, by adding the atomic masses in accordance with that empirical formula, we will get a sum, which is the atomic mass of various atoms present in the empirical formula. So the formula we got is CH2Cl. According to that, if you calculate the mass, then it will be 12.01 plus 2 into 1.008 plus 35.453, which is equals to 49.48 grams. Next, we have to determine a factor, and that factor is got by dividing molar mass by the empirical formula mass. So this is not the molar mass, this is the empirical formula mass that we have calculated for CH2Cl. If we do so, we will get 2 as the factor that we are searching for. Now, we can get the molecular formula by multiplying 2 across the stoichiometric coefficient of each of this element. If we do so, what we will get? We will get C2H4Cl2. So simple, carbon has 1 as the coefficient, so 2 multiplied by 1, C2. H has 2 as the coefficient, so 2 multiplied by 2, which is 4. And Cl has 1 as the coefficient, so 1 multiplied by 2, again 2. So we have now the molecular formula as well as the empirical formula. Then moving on to the next thing, which is stoichiometry. Now the stoichiometry is defined from 2 Greek words. First is stoichion, which means element, and second is metron, which means measure. So with the help of your stoichiometry, you get the amount of element in a given reaction. Thus, we can say that our stoichiometry deals with the calculation of masses of the reactants as well as the product across a chemical reaction. And in some cases, we can get the volume also. Now, for that, we will consider the combustion of methane. The balanced chemical equation for that combustion would be CH4 2O2 gaseous. So in the presence of oxygen, we are combusting it to get CO2 and 2H2O. Then, what are the reactants and products in our given reaction? Methane and dioxygen are the reactants, whereas carbon dioxide and water are the products. Now, remember that all the gases are represented with the help of a G inside a bracket. And here, all the gases that are present are reactants and products. Means all the constituting species are gases. Okay. We can do the same thing for solid and liquid if we have a solid or liquid in the reaction mixture, but here we don't have. The next thing we know is that the balanced chemical equation here has 2 as the coefficient for oxygen, and for the H2O also we have 2 as the coefficient, stoichiometric coefficient. Similarly, for CH4 and CO2, the coefficient is 1. Now, what do this coefficient represent? So, there is a confusion in the minds of children that it represents only moles, or in some cases they think that it represents only molecule. But remember students, it is very important to understand that this stoichiometric coefficient is defining both the molecules and the moles. How can we understand it? So according to the chemical reaction, we can say that since it has a coefficient of 1, our methane, then we will say that 1 mole of methane reacts with 2 moles of oxygen to give us 1 mole of carbon dioxide and 2 mole of water molecule. Now this is about moles. Now the same thing can be said for molecule, like 1 molecule of methane reacts with 2 molecules of oxygen to give 1 molecule of carbon dioxide and 2 molecules of water. Since our elements or the compounds are gaseous in nature, and if we take them as the ideal gas, okay, remember they are the ideal gas, and if it is given, so in this case, we will take 22.7 liter of CH4. So what is this 22.7 liter? Where it is coming from? So for this, you have to understand that if you take 1 mole of a gas, and in most of your calculations, you will use the same liter. Remember, maybe ideal gas would not be mentioned here, but if gas is there, And the conditions are standard. What is standard? 1 is the atmospheric pressure and 298 Kelvin is the temperature. Then 1 mole of any gas will contain 22.7 liter. Means it will be having a value of the volume as 22.7 liter. Now, if you double the mole, the volume will also be doubled. Okay. But for CO2 it is 1, so it will be 22.7 liter for CO2 and 45.4 is for H2O. So we have just multiplied 22.7 with 2. So we can finally see that 22.7 liter of methane reacts with 45.4 liters of oxygen to give 22.7 liters of carbon dioxide and 45.4 liters of water vapor or H2O gaseous. Then we know that 1 mole of methane has 16 gram mass. Therefore, we can say that 16 gram methane reacts with, again, the mass is been taken for oxygen also. So 32 gram of oxygen will react with 44 gram of carbon dioxide to give us 2 into 18 gram of H2O. Okay, so here we have 2 into 32 gram of oxygen. Not 32, it is 2 into 32 because we have 2 moles of oxygen that has been taken. So for one atom, 16 is the atomic weight. For a oxygen molecule, it will be 32, 16 multiplied by 2. And for 2 moles, it will be 2 into 32. Same thing can be said for the water. You can just try and calculate the molar mass. You will get the same thing multiplied by 2. So from these 4 statements, we can say that mass, moles, and number of molecules, each of this can be represented with the help of the stoichiometric equation. Now, why we have not written the volume thing? Because we are able to know the volume thing as all the constituent species are gases. If it was not so, we won't be getting this volume. Therefore, I have taken only mass, moles, and number of molecules. Now, coming on to a next thing, which is limiting reagent. So, many times the reactions are carried out with the amount of reactant that are different as per the balanced chemical equation. Suppose our one of the reactant is present in a small amount in accordance to the stoichiometric equation. So in such situation, the reactant which is more in amount will be the one which is the dominating one, and the one which is left or which is in the least amount will be the limiting thing. Okay, again, suppose we are saying that 1 mole of water requires 2 moles of CO2 for any arbitrary reaction, but we have only 1 mole of CO2. In that case, your CO2 will be a limiting reagent because it is present in a small amount. So, in that case, your limiting reagent will be consumed wholly, and the one which is present in excess will be left in the reaction mixture. So, this concept is known as limiting reagent. So, when we will do some problems on this limiting reagent, you will get a clear picture of what it is. Moving on to the reaction in solutions. What does reactions in solution mean? So most of our reaction that we do in our laboratory are done in the solution phase. And to represent the amount of solute in a given solution, we have different ways. First is mass percentage or weight percentage. Second is mole fraction. Third is molarity. And fourth is molality. Now we will look at each of these concentration terms one by one. So mass percentage is related to the concentration of a solution or the proportion of component in a mixture. What does it mean? So you can think of it similar to the percentage composition, but here you don't have a fixed value. As in the case of a compound, you have the fixed value of the element. So it will depend on the reaction mixture you are dealing with. Suppose you have to calculate the mass percentage of solute. How you will calculate it? You will simply take mass percent of solute divided by the total mass of the solution. So you will take mass of solute by mass of solution multiplied by 100. So this will give you your mass percentage of the given solution. Let us do a question on it to understand it more carefully. Suppose a solution is made by adding 2 gram of a substance to 18 gram of water. Then what is the mass percentage of solute? To calculate it, we will simply use our formula, which is mass percentage of this A thing or the substance A can be given as mass of A by total mass of solution multiplied by 100. So this was our equation. If you put the values of mass of A, which is 2 gram, and total mass of the solution will be mass of water, which is the solvent, plus mass of solute, which is the substance A. So 2 plus 18 will be 20. 2 by 20 into 100 will give you 10% as the mass percent of A. Very simple to calculate. Now, next thing is mole fraction, and it is simply the number of moles of a particular component whose mole fraction you are interested in divided by the total number of moles in the solution. Suppose we have A dissolved in substance B and their moles of A and B are Na and Nb. How can we calculate the mole fraction of A and B then? So mole fraction of A can be calculated by number of moles of A by total number of moles, which is Na and B. Now you can represent the mole fraction of A with the help of a symbol which is chi. So you just write chi and write A in the subscript. Okay, so this will be equals to chi A. So this is not X, it is different from X. The same calculation can be done for the mole fraction of B. So it will be number of moles of B divided by the total number of moles of the solution. Again, this is equated to the mole fraction of B or chi B. I hope you are getting my point of this mole fraction. Now this mole fraction is much more meant for the gaseous mixture rather than the liquid solutions, as gases are more well defined with the help of moles rather than the volume, as their volume is indefinite. Our next and the most popular concentration term is molarity, which is represented by capital M. The definition of the molarity is number of moles of the solute present in 1 liter of the solution. To calculate it, we will simply take the volume of the whole solution in liters and put it in the denominator. In the numerator, we will take the number of moles which is dissolved in that volume. Okay, the number of moles of solute which is dissolved in that same volume of solution. Now suppose we got 1 molar solution. What does it mean? And suppose it is for NaOH, and we want to prepare 0.2 molar solution from the same 1 molar solution of NaOH. So by 1 molar NaOH, we mean that 1 mole of the solute is present in 1 liter of the solution. As simple as that. Okay, so 1 molar NaOH means 1 mole NaOH dissolved in 1 liter of the solution. If you put this values here, then only you will get 1 molar as the concentration. So how do we make it 0.2 molar? For that, we need to dissolve 0.2 molar in 1 liter of solution. Okay. So to achieve this goal, what we will do is we have to dilute the solution, because initially we have a greater concentration which is 1 mole per liter. Now we have to make it to a smaller concentration which is 0.2 mole per liter. Now how much volume of the concentrated solution should be taken which contains 0.2 moles? So we said that 1 mole is present in 1 liter. Then 0.2 moles will be present in. So we can calculate it by using this equation. So 1 mole is present in 1 liter. Okay. So we can write it as 1000 by 1 to calculate the moles in 1 liter. Okay. Multiplied by 0.2. So 0.2 moles will be present in 200 ml. Again, we can write 1 liter as 1000 ml. So we have used the same thing. So if we say that 1 mole is present in 1000 ml, then in 1 ml, how many moles will be present? 1000 ml by 1. So for 0.2 mole, we have to multiply this thing by 0.2. You will get 200 ml solution. Now, in 200 ml solution, we have 0.2 mole. If we add water to this 200 ml and keep on adding it such that your volume becomes 1 liter, then we will say that, okay, the number of moles is not changed in this process, but the volume of the solvent has increased. Therefore, our new molarity will be 0.2 molar. I hope you're getting the point which I am trying to make here. You just have to think this calculation once again. But this process is very tedious. So we will use a general formula to calculate the same thing, which is given as M1V1 equals to M2V2. In our previous case, suppose we have M1 as 0.2 ml, okay, and V1 as 1000 ml, whereas M2 has 1.0 m and V2 is to be calculated. Means we know that 0.2 molar solution is needed and its 1000 ml is required. We know that 1 molar solution is given to us, but its volume is unknown, that how much volume should we take for the same calculation. So we will use it, which is M1 into V1 by M2 into V2, so 0.2 into 1000 ml, 1 into V2. This will give your volume as 200 liter, or we have converted this thing into liter, you would say. So this will be 200 milliliter, not liter, it will be 200 milliliter. Therefore, we again got the same thing which we are getting in the previous case. So 0.2, even after dilution, as we have changed just the amount of solvent, we have not played with the number of moles of solute. Therefore, we will get 0.2 molar as the concentration. Now, let us do a question to understand this thing. Our molarity of sodium hydroxide is to be calculated, where we are dissolving 4 gram of NaOH in 250 ml. So we use the formula molarity is equals to number of moles of solute by volume of solution in liters. Now, the number of moles can be calculated by given mass of NaOH by molar mass of NaOH. So 4 gram. So NaOH has a molar mass of 40 grams. So 4 by 50 gives you the mole. This milliliter can be converted to liter by dividing it by 1000. So if you do so, you will get 0.250 liter. Do your calculation, you will get 0.4 molar as your what? As your final molarity. Remember, since molarity is including your volume and volume is dependent upon temperature, so you can finally say that molarity is also dependent upon temperature. Our next concentration term is molality. Now, the numerator of molarity and molality is same, which is number of moles of solute, but the denominator is different. In molarity, we have 1 liter of solution, whereas in molality, we have 1 kg of solvent. This thing is denoted by small letter m, not by the capital letter M. So, the formula would be number of moles of solute by mass of solvent in kg. So, often in a chemistry lab, a desired concentration is prepared by diluting a solution of known higher concentration. So, that solution which is of a higher concentration is known as stock solution. So, in our previous case, we have done the same thing. We have taken a solution which was of known concentration and it has a higher concentration, then we have diluted it, okay, by taking 200 ml of it and dissolving it with further solvent to make it as 1000 ml. So there we have taken the stock solution of 1 molar and we have got our required solution of 0.2 molar. But remember, since molality is independent of your volume and is dependent on the mass, therefore it is not a function of temperature or it has no effect of temperature change. Now we'll do a question related to it. Suppose the density of 3 molar solution is given as 1.25 gram per milliliter. Then how we will calculate the molality of the solution? So we already have the density. So we'll use the formula of density, which is mass per unit volume. Our molarity is 3 mole per liter. Then what is the mass of NaCl in 1 liter? So by molarity 3 mole per liter, we mean that 3 moles is present in 1 liter. Okay, and 3 mole has a mass of 3 into 58.5, which is the molar mass of NaCl multiplied by the number of moles. So in 1 liter of the solution, we have 175.5 grams of sodium chloride. Then our next thing is to calculate the mass of solution, because for molality we need the mass of solvent. We already have the mass of solute. If we calculate the mass of the solution, we can subtract both of this to get the mass of the solvent. So we have done the same thing. 1000 multiplied by 1.25. Why we have multiplied it by 1000? Because we are trying to convert our milliliter to liter. Okay. Because this mass is present in 1 milliliter and we need the same mass in the liter. So we multiply it and we get that 1250 grams is present in 1 liter of the solution. It's very simple. We are converting this gram per ml density to gram per liter solution, and then we get the amount of substance dissolved in 1 liter. So this is very obvious from the unit as well. Now, since your density is 1.25, we have done this thing. Our next goal was to calculate the mass of solvent. So it will be 1250 minus 75.5, which will give you 1074.5. Lastly, your molality will be number of moles by mass of solvent in kg, which will be equals to 2.79 small m, which is molality. So this was all for today's lecture. Thank you for joining the session.